Okay. Sorry, just confirm. Can you guys actually hear me? I switched mics and I'm not sure if it's working. I assume not then. Okay. Okay. I think we can get started then. If people aren't here from your team, that's okay, because I am recording it and I will upload it to YouTube. So you won't miss anything. You can check on there, and then depending on how keen people are, I can also do a kind of Q&A helping with specific issues. Maybe in the middle of the week after you've had some time to experiment with the stuff yourself. So welcome to the first Starter Bot programming session. As you would have seen from the message and announcement on the Ignite Discord, this is to help you get kick-started when programming your starter kit. Because the starter kits have been slightly delayed, unfortunately, in terms of getting here, it's a good idea to get started now with programming so that when it arrives, it can all happen quickly and you'll be ready in time for the competition, which I think you'll still have more than enough time. So yeah, that's the good news as well, though, is that the starter kits, the first batch of starter kits have been shipped, so they should be here in the next week or so, which is great. Exciting stuff. But yeah, so today what I'm going to do for this first section, I'm just going to walk through kind of the hardware that is going to be in the starter kit, the robot you're going to have, and then the best way to go about programming it. For this session, we'll probably just stick with teleop, and we probably won't go do the full teleop. And then next week and maybe the week after, probably 3 weeks maybe, we'll finish off the teleop and then talk about autonomous as well and the possibilities there. So first thing I want to do is to just keep tabbing to the wrong screen. Is to just show you here. So this was the kit that is being shipped out, as most of you have probably seen. It's the Gobilda starter kit for the 2024-2025 season. So you get like a chassis, you get like some structure stuff, some motors, some servos. And then the nice thing this season is that Gobilda has put together a starter bot that actually can compete in the season. So this is the starter bot right here. It's only comprised of parts that come inside of the starter kit. And the nice thing about this is that it's a great way to get started in FTC in your first season. I think for us as TechSpan, it would have been, if something like this existed, we would have really enjoyed it. But unfortunately, it didn't exist back then. We just got a kit apart and had to figure it out. But this is a very nice starting base. And I would suggest as well, I want to watch a video now of what it is in terms of the hardware. But I would also suggest you going and checking out this yourselves. And also check out the robot in 3 days by Gobilda, because they actually start with the starter bot and then build on top of it. So that's the nice thing about this, right? Is it gives you a really solid base. It allows you to perform in this season's game actually pretty well. It's actually, after exploring it a bit myself, I hadn't looked at it very much, but it actually is a really cool bot. It actually can be quite a competitive bot with enough driver practice and then some of your own like innovations on top of the design. So let me just see here. Where is the Gobilda video so I can show you? Because I want to watch. Oh, here we go. So I want to just watch this quickly because this meeting is about programming of the robot. But when you're programming it, obviously it always starts with the hardware. So it's good to understand what hardware you're going to have and what way you can control it before we actually jump into the actual code for it. So I just want to play this now quickly. Here, so you can just get to grips in terms of the hardware.
Hey guys, I'm Ethan with Gobilda, and today...
Can you guys hear it through the stream?
I'm going to show you the FTC Starter Kit robot for the 2024-2020.
That's strange. Let's see. I'm going to stop sharing and see if I have an option to share with audio. Tab instead. Oh, so I can't actually share audio because you can't actually share audio for without Chrome tab. So what I'm going to do is I'm going to open this in YouTube.
Hey guys,
Quickly take the link, put it in here, and then share this tab.
Hey guys, I'm
Okay, you should be able
the Starter Kit robot.
Here. Should be able to see this now. And then let me know if you can hear
For the
this.
2024-2025 First Tech Challenge season. Hey guys, I'm Ethan with Gobilda, and today...
Can you hear that? Okay, you can. Okay, cool. So yeah, I just want to run through this quickly so you get it's just a 4-minute video, a brief understanding of the hardware involved in this. There's also an assembly guide which you can also have a look at. I can send links for this in the Discord as well after the meeting, so you can check it out yourself.
Today I'm going to show you the FTC Starter Kit robot for the 2024-2025 First Tech Challenge season, Into the Deep. Before we jump into exactly how this robot works, let's talk about the concept. This is a robot that's built entirely out of parts you can find in the FTC Starter Kit for this season. Now this is a new concept because it is game specific. It's designed to interact with the game elements that are specific to this year's game, score them, and it can even hang in endgame. Now this robot has assembly instructions, it has CAD and example code, so that it's really easy to get up and running and we can really raise the floor of the competition for the First Tech Challenge. If you have a Gobilda starter kit, you can build this robot because we want to lay that foundation and allow you to iterate upon it. This robot isn't going to win the World Championships, but it's going to give you a foundation of a robot that can score, which you can then take and make awesome with your own inventions. Now let's jump into how this robot actually works. There are two kinds of scoring elements in this year's FTC season. You have samples, and you can take a sample and create a specimen by adding a hook. This robot is able to score both of them, but let's talk about samples first. Looking from the ground up, this robot has a 6-wheel drive drivetrain, a tower that supports this arm, which is powered by a motor. This arm is the primary way you interact with scoring elements, and it gives you this movement vertically and horizontally. On the end of the arm, you can see our end effector. This is an active intake powered by a speed servo in continuous mode, so it'll continuously rotate, and that speed servo is powering a gecko wheel. Now we cut the rim off this gecko wheel to grab these specific elements a little better, and we recommend you do that too. You can just grab some scissors and chop in between the ribs that support the outer ring of that gecko wheel. When you turn the servo on and you interact with the sample, the servo will pull it up into this basket made of low channel and hold it there. You can even turn the servo off and it's constrained pretty well. You can then raise the arm and run the servo backwards to deposit that sample. Now, like I mentioned, this is designed best for that low basket. Some additional extension is probably possible to add to this robot to get to the high basket, but for this, we're really hoping to just get you scoring and get you moving toward a solution that your team has made. Now, you'll notice this torque servo here. It is on a compact servo block, and it allows this intake system to pivot. You can collapse it in, and this is used in two ways. Firstly, it allows the robot to fit inside that 18-inch starting configuration, but it also allows you to score specimen. If we grab a specimen with that intake, we can then raise the arm and pivot the wrist out. This allows us to hook the specimen onto the chamber and just drive away, leaving the specimen securely scored. Now, scoring specimens requires a little driver precision. There's a fairly narrow range where you can intake this element, so it'll take some practice to be able to do it consistently. We think this is a great starting place for some iteration, and it's totally possible to do, but you gotta make sure that you practice if you expect to do it consistently in competition. Now, the last piece of functionality for this robot is its ability to hang. It has this channel right here, which can hook on the lower rung, and it can pull the robot up with the arm motor. It's got plenty of torque, so you really don't have to worry about overstressing this motor at all. Now it can extend to that lower rung, which is a level 2 hang, which gets you a lot of the way there. I'm sure it's possible to add some functionality to this robot to get to that level 3 hang where you're fully supported by the top rung, but that's a little out of the scope of this starter robot. I briefly touched on the drivetrain earlier. It's comprised of two 312 RPM motors, which power 4 Rhino wheels. Each of these Rhino wheels are driven with chain or a gear system, and it has 2 Omni wheels, which just free spin. These give you that little bit more maneuverability, and critically for a robot like this with a long arm, it gives you that extra support that you need to not tip over. Like I mentioned earlier, this has CAD, it has assembly instructions, and it has code, which you can all find on our website if you head over to the starter kit page. We're super excited with how this robot turned out. If your team builds this and iterates on it, please let us know, tag us on social media, because we're excited to see how you take this robot and improve upon it. If you have questions about this robot or other parts we sell at Gobilda, feel free to shoot us an email over to tech@gobilda.com.
Okay. Wait. Okay. Wait, is my mic working now? I don't think it is. Great. No, I think it is actually. Okay, cool. Perfect. Thank you for confirming that. Let me share the other screen. So you can see like how versatile this robot can actually be, and how, like he was saying in the video as well, it's a great starting place and a good kickstart, especially for first year teams, rookie teams. Because with this bot and a good amount of driver practice and some nice software, you can actually be way above average in the competition in South Africa for sure. Especially with, yeah, like it's not just how complex your robot is that's gonna determine if you do well. It's actually just mainly determined by having a solid design, having it finished relatively early, and then doing software and driver practice. That's really going to put you or set you apart from the average C. You know what I mean? So this is very useful because now in the starter kit, right? They give you a whole lot, like he mentioned in the video. They give you a whole lot of resources. Like they give you some. I've already got it open here. You've got assembly instructions on how exactly to put the robot together. Obviously not really in the scope of what we're doing today, but that is very useful to get it up and running. And then they've actually got the example code as well in a GitHub repository. So that's what we're going to go through today, is like with the hardware in this bot, walking through what we need to control, why we need it, and then actually implementing it in Android Studio is the plan. So what I want to start with then is the chassis, and we did go through a lot of the code that we're going to go through in the previous Ignite training sessions, but I think it's helpful to just walk through the process of going, here's the hardware we have, how do we turn this, or how do we create code for this hardware that intelligently controls it and makes it easy for the drivers to use and understand how to use the robot. So the first thing I want to do then is, let me share Android Studio. You know what? I'll probably just share my whole screen. It's going to create some weird stuff, but it's fine. There we go. The infinite thing. So if we hop into Android, no, not that, Android Studio. The first thing we're going to want to do, right, is here, you should have Android Studio set up looking something like this. The README will be open. You should have your team code folder in your Java folder. And then inside this folder right here, org.firstinspires.ftc.teamcode. So what we're going to do is we're going to start with a Atelier, right? So I'm going to say new Java class Atelier. You know what? Let me rename that. Let me be a bit more specific. Let's say starter bot Atelier. Someone else trying to get in. Let me see. Yes. Let me stop sharing. It's going to be much easier to share just Android Studio. There we go. Okay. And I'm going to just go through some from the beginning, getting through what you're going to need. Now you've actually got the hardware. You know what hardware you need, your config, I'm not going to be able to show you the config, obviously, because I don't have the robot or our robot here, but I can talk you through the process. If at any point you don't understand something or you want me to explain it in more detail or I'm going too fast, please just let me know, because that's the whole point of this. I'm trying to make sure that I can explain it in such a way that everyone can understand it. So I'm going to do more general overview now of kind of the process, and then, yeah, like I mentioned, maybe do something in the middle of the week that's slightly more specific to whatever you're busy working on. Okay. So we start with this teleop, and as normal, the first thing you would do, right, is you have your class here, and you have the name of your class or your program or your teleop in this case. So the first thing you need to do is you need to extend op mode. And this allows you to have the loop and the init for where your initializing code and your driver control code is going to go. So the first step is, like I mentioned, is actually once you have your hardware, in this case the starter bot, you actually need to add it to your configuration on the robot. So what this means is that you need to tell your code what port are we communicating with, right? Because on the control hub, you have 4 ports, the control hub being the, you know what, it's best if I do share my whole screen, because then I can show you an actual example. But the control hub being the place that actually stores your code, runs your code, and where you plug in all your hardware, like your servos or your motors. So that would actually be the first step. You need to have a way of telling your code what ports are we actually controlling, because there's not a specific port you plug in for each motor. So you can have your drive motors, but they could be plugged into any of the ports on the hub or the brain of the robot. So you actually need a way of telling the robot what port to communicate with or control. So the first thing I'm going to do is actually, before we can actually do that step, is we actually need to create our motors. So I have caps lock. DC motor, we're going to say left, right. Okay, just going to do this. I'm just going to copy it. So now we're going to have our 2 drive motors, right? Like we talked about in the other training sessions, it's an omni-wheel drive, so we only have 2 motors, one for driving the one side, one for the other side. It's the same as controlling a normal omni-wheel drive, except this drivetrain actually has 6 wheels, but it works exactly the same. So now we actually need to tell these motors what ports are we actually controlling. So the way you would do that in the code, you say left drive equals hardware map dot get DC motor. This is the type, right? DC motor dot class, comma, and now this is the name that you need to put in here. This is the name of the port, that you want to control. So on the control hub, you have the ports 0 to 3. For motors, you have 4 ports for motors. And let's just say, for argument's sake, that you've plugged in your 2 drivetrain motors into ports 0 and 1, right? And then in the configuration of your robot, I can maybe send you a link to actually how you do the configuration, because I don't, yeah, I can go through it now quickly. Let me just find it. I didn't actually think that I would need this. Okay, here we go. Because now you actually have the port, right? You got this thing called your configuration. I did talk about it a bit in the other training sessions, but I want to just make sure I go through this now so we're not skipping any steps. So if I just share this now quickly, Chrome tab, here we go. So what you're actually trying to do here is that you have, this is configuring a motor, right? You have this like UI screen on your control hub or your driver hub, which is what actually runs your robot, right? So this is your configuration screen. So what you do is you push on motors, and then you can see on the right here, you have ports, like I was talking about, ports 0, 1, 2, 3, right? And then where it says nothing, you would click on that, and it gives you a drop down menu, you can see here, of the types of motors. So then you put in the type of motor you have, and then down here you put in the name. And this motor name is basically naming the port, the physical port, a certain name, and then you use this name in your code to control that specific port. So in our case, we'd say up here where it says Tetrix motor, we'd say Gobilda motor, and then down here in the motor name, we'd say left drive, right? And then what we can do when we go into Android Studio and are actually programming it, we want that name that we named the port in our configuration to be put in those double quotation marks. You can see here it says device name, right? So this is the name of your hardware device inside your configuration. So in here, we'll say, okay, left drive. So this is a part that you can't actually do the configuration now until you get your starter kit and you have the robot. But you just need to understand how it works so that you can have the code set up in such a way that it needs to be set up. And then what we normally do in TextMan and most teams as well is that you would actually program the names here. You would program it in Android Studio first, and then you would go and create your configuration and use the names you put in this double quotation marks in your configuration. So not the other way around, because the configuration is a bit of a pain because you have to type on a weird keyboard, pop-up keyboard, and sometimes it deletes itself. So that's just the way around we like to do it, just to make things simpler. So I'm just going to copy this then and call this one right drive. We need to do this for both motors right here, and we're going to say right drive over here. Okay, and then the other thing you want to do is that for teleop, we're not actually going to be using the encoders. So basically the encoders are things on the motor, on the back of the motor actually, that count little things called ticks. So it counts a certain amount of ticks per rotation of the motor, and that allows you to figure out how far has the motor rotated. So for instance, if the motor counts 200 ticks per rotation, then if you know that if the motor has traveled 100 ticks, right, it's traveled 180 degrees, half a rotation, because that's half of the overall ticks that the motor reads per rotation, if that makes sense. But for the driving in teleop, we're not actually going to use the position. We're just going to set it to a power, just drive in a certain direction based on what the driver wants us to do, right? Again, this is all stuff I covered in our other training session, but I just want to make sure I go through it again. So it is a bit of a duplicate, but I think it's important. So we're going to say left drive dot set mode. Because we don't want to use the encoders, we're going to say run without encoder. And then right drive as well. So we're setting them both to run without encoder. This doesn't mean that you actually can't get the position of the encoder if you ever want. It just means that it's not going to like use the encoder to set the power of the motor. So that sometimes in FTC, if you run with the encoder, the motor power that you actually set the motor to is not necessarily what it's actually being set to physically. So it's just easier to set it without encoder right now, so it doesn't do weird stuff while we're working on it. Okay, so now that we have those set up, the next thing is to actually go into this loop code, right? Inside the curly braces, your code always goes inside the curly braces. And inside this loop thing is where we're actually going to get input from the driver and decide what to do with that input, or use that input to almost make decisions for the robot or control the robot based on those decisions. So the first thing here is we actually need is the input from the drivers. So how you get that is you say gamepad 1, right? But actually what you need to do first, and this is something that we didn't cover a lot in the previous programming guides, is actually like creating a variable and what exactly does a variable do. So a variable in FTC, the only thing we rarely use them for is to store values, right? And that's what it's used for most of the time as well. But basically what you do up here is you can say a type of a variable, which is just storing data, or in FTC it's just a value. So we would say double. So double stores a number with a decimal point. So the driver can input on the joysticks because we want the driver to be able to control the drivetrain on the joysticks, right? So the driver input from the joysticks is when the joystick's pressed all the way up, it'll be 1, and when it's just set, when it's not being pushed, it'll be 0. And then it'll go negative the other way. So a double allows us to store the position anywhere between. Say if the driver pushes the joystick halfway up, then it will store a position of 0.5, right? So we just want to have a variable that can actually store that value that's being inputted from the drivers. So what we'll do is we'll say double, and then we'll call it vertical. So vertical meaning the forwards and backwards movement of the drivetrain, right? And then we'd need one other one saying turning. So these are just two variables, as we call them, to store data from the driver input. So what we can do down here is you always create your variables up at the top above your init and your loop code. And then you can access them in your init and loop code. So in this case, we'd say vertical equals, so we're setting the vertical, right? We're storing the gamepad input in the vertical variable. So we're saying left stick Y, we actually want right stick Y. So the right stick of the gamepad, we want the Y is the up and down, and we want that to control the forwards and backwards. I mean, if you would like to, you can use different joysticks. That's just a normal convention. And you actually need to say, you actually want the opposite of this value, because what happens is for a gamepad in FTC, it actually inputs -1 when you push it up and +1 when you pull it down. Only for the vertical ones. The sideways ones is positive when it goes to the right and negative when it goes to the left. So for this, we actually need to take the opposite of the value because we want it to go positive when we push it up because we want the robot to drive forward, right? That just is what's most intuitive for the drivers. So the way you would take the opposite of this value is you would just put a minus sign or a minus sign in front of the value. And this just inverts the value. So if the driver pushes up on the gamepad, the gamepad will return like -5, -0.5 if it's halfway up. But the minus sign in the code is going to make it turn it into a positive number. So it'll be positive 0.5. And then we want the same thing for the turning. Except now, normally what we would say, it would say the left stick X. And we don't want to take the opposite. So we take the negative sign away. And this means that for the right stick, if you push it forward, the robot will go forward. If you pull it backwards, it'll go backwards. And the turning will be on the joystick on the left. If you push it to the right, it'll turn to the right. If you push it to the left, it'll turn to the left. So let me just pause there for a second. Has anyone got any questions before I go on to setting the motor power? And you're welcome to unmute yourself and ask them in the voice chat as well. Okay. If not, then I'll continue. So now that we actually have the values or the direction that the driver wants to make the robot move, we can turn it into the actual motor powers. So because we want to have it so that the driver can, if the driver wants to move the robot forward and turn at the same time, they need to be able to do that. So we can't set them, oh, if vertical is not equal to 0, meaning the driver actually wants to move, then set the motor power to this. And if turning is not equal to 0, meaning the driver wants to turn, then set the motor power to the turning one. That means that the driver can't do both at the same time, which is quite limiting. So what you need to do is you need to say left drive, right, dot set power. So this is the setting the power of the motor. And then you're going to say for the left drive motor, oh, wait. I missed something important over here. In the initializing, I just need to add this in before we go on. You actually, because the motors are pointing in opposite directions in the drivetrain, they will spin in different directions by default. Because they both spin clockwise by default, when you set them motor power to 1, they will go in opposite directions because they're pointing in opposite ways. So you actually need to reverse one of the motors. So in this case, you would probably you need to reverse the left motor, because the right motor default is clockwise, which means 1 is going to push the robot forward. Positive power, sorry. So what you want to say is you want to say left drive dot set direction to reverse. That just allows it to make sure that when you set both motors to positive 1, they both go forward. So then we have left drive and we have right drive. So what you want to say is you want to say vertical, and then you want to say for left drive, if you're turning to the right, you want your right motor to be reversed and your left motor to be forward, which means that you should say left drive is vertical plus turning, because that means that if this is a negative value, it's going to make this go more negative, right? So what I'm saying is negative in the turning is going to mean that the left motor needs to go reversed and the right motor needs to go forward, which will turn the robot to the left. If you want to go to the right, which is positive turning power, then you want your right motor to be reversed and your left motor to go forwards. So then for the right motor, you would say vertical minus turning. Okay, so this is actually all the code you need for the drivetrain. It's quite straightforward once you get your head around it. Then, so this will be like the base, right, for your teleop. We're going to talk more about in probably next week's meeting, probably Saturday sometime as well, maybe a slightly different time. I'm going to talk more about the autonomous programming and stuff like that. But for this week's session, for the code, this is all you're going to need for your teleop code. Like I said, we talked about in other sessions. So it's not so interesting. But now, if everyone understands that and is at grips with that, please, if you don't, please let me know now so that I can try and make it more clear for you. Because I don't want to go on if you're still confused about this. Because that's the whole point, is to just make sure that everyone, because I know that from experience, all this stuff can be very daunting when you're first starting. So I just want to make sure everyone's in a good headspace and understands everything as best as possible. Oh, thanks. Glad you enjoyed it. Okay. Seems like everyone's fine with that. So what I'm going to do is I'm going to go back to... Wait, where is the... I think it's this tab. So I'm going to share the Google tab again. So now we've got the drivetrain code, right? This is going to allow us to control these drivetrain. You can see here the two motors that we're controlling. We've got the left motor and the right motor. So that's all done. So the next thing that we would need to program, right, we're just going to keep moving up here along, is this motor right here. And this motor is what controls the arm's tilt, right? And now what we need for this is that we need some way of knowing where the arm is so that we can tell it where we need it to go. For instance, we need a collect position. You can see this down here by the ground is where you would want to intake the samples or specimens. And then you want one that, I don't think there's an example of it here. Okay, here. You want a position that goes up to here, right? To hold this position. And this is where the motor encoders, like I was talking about earlier, this is where these come in handy. Because there's a motor encoder built into the robot, into the motor, sorry, we can use that to know where the arm is. And this is where the example code from Gobilda becomes useful, because the example code from Gobilda can help us get the correct, convert the ticks of the motor to a position for the arm in degrees, right? So how motor encoders work is that wherever they start, that position is set to 0, right? And then everything from that is relative. So you can change the direction of the motor, which also changes the direction of the encoder, which means that if you start at 0, then one way will, if you move the arm the one way or the motor the one way, then it will count positive ticks on the encoder, right? And then if you go the other way, it'll go negative ticks. Now, like I was saying, to actually find a position for dropping off and stuff in degrees, which we can actually understand in degrees from the start position, the motor measures it in ticks, which is not a very helpful metric for us. It doesn't tell us, it doesn't quantify the amount it's going to move very helpful, very in a way we can understand, right? So that's where this example code comes in helpful. Basically, this is a GitHub repository that has this code on it. I think it's quite overcomplicated, so that's why I don't suggest just going and using it. But it gives us this calculation here. And you can see here, this is arm ticks per degree. So this will convert the ticks of the motor into degrees, which means that then we can set the motor's position in degrees, which is what we can understand better. So what this is the one thing I would suggest using out of here, because you know they know the exact gear ratio. So this is basically finding the gear ratio, and then it's the gear reduction, because you can see over here on the, oh no, that's not working. You can see over, why does it not let me zoom in? Okay. I don't know why it doesn't let me zoom in. Let me see if I can. You can see here. You can see right here, right? This little black cog over here, this is on the motor shaft, and this big silver one is on the shaft that the arm is moving on, right? So this means that it's going to make the motor, because it's small gear to a big gear, it's going to make the motor move slower, but it's going to be powerful enough to actually hold it up there. And for an arm, even a motor, like for a normal drivetrain motor, for these drivetrain motors, the motor spins at 312 revolutions per minute. But for the arm motor, a really fast arm can normally spin at around 50 revolutions per minute, which is a lot slower, but it doesn't actually have to spin all the way around because it's just moving the arm like so. So that's the next thing we want to do, right? And to start, we need to go back to Android Studio. We can take this line of code that gives us the arm ticks per degree, and we can put it up here, right, where we define variables. You can see it's also a double, so it also stores a number with a decimal point. Let me just put this all onto the same line. They've added a whole lot of commenting here. Okay. So we're going to just remove the commenting. And now we have this variable, right, called arm ticks per degree. So now we can use this to actually convert it to a value that we want to move to the arm to. So the first thing we want to actually do is to create our motor, right? Because it's controlled by a motor. We're going to do the same thing here. We're going to say DC motor, and we're going to give it a name. So we're going to say arm motor, right? Let's just call it arm motor. And the same thing happens here. We need to tell it what port are we actually communicating with, right? We're going to say arm motor equals hardware map.get DC motor.class, and then in here we're going to say arm motor. We're going to assume that, and like I said, the way around we would normally do it is that we would put the name in here, and then once we fully programmed everything, we would do our configuration and put these in the correct port locations in our configuration so that it controls the correct motor. Then for the arm motor, you actually want to set it slightly differently because we are using the encoder in the motor, well, in the arm, which is controlled by the motor. We actually want to do something slightly differently. We want to go here. We want to say arm motor.set mode first you want to say stop and reset encoders. So that basically is what actually makes sure that the position where our arm starts is always going to be 0, right? And that means that when we always start with the arm in the one place, we can actually it'll always go to the same position every time. So that's the first thing we need to do. Then after that, we can say arm motor dot set mode to run to position. So basically this run to position mode is very helpful built-in code already in the SDK. That means we have to program stuff a lot less. And it works pretty well for an ARM control, especially the Gobilda ARM. So what this does is it actually will drive the arm to the position you want it to, right? Let me just admit that. Okay, cool. So without us having to like find the motor power to set it to, and then like, often when you have that, you need a specific type of controller, which I'm not going to talk about, but it's quite a lot more difficult. But luckily for us, there's already a built-in way of setting the arm to a target position, right? So now what we want to do, we have the arm's motor set up, right, in run to position, and we have the arm ticks per degree. So now what we want to do is we want to create some more variables that store the target positions we want to go to, right? So if I share the Gobilda stuff again, where did it go? Here we go. We're going to want a couple target positions, right? We're going to want our collection target position. Wait, oh man, wrong place. Here. So we're going to want our collection position for the arm, right? Which is all the way over here. And we're going to want a delivery position like this. One for the basket and one for the chamber for clipping. And then we also want this is the starting position, right? This is what will be set to 0. So what we need to find is we need to say how many, and this is a bit of trial and error, but because it's in degrees, it helps a lot. So if we're saying this is the starting place of the bot, right? This is 0. We want it to be sticking out the top here for delivery, right? For the basket. And the basket and the chamber are going to be pretty similar. So we want to set out the top. So if we go completely to this side, it's probably about 180 degrees, maybe 170 from this position, right? So it's not quite half a rotation. So it sticks up here. And then this position right here, I mean, is probably around 250 degrees from the starting position, flipping over. I mean, again, this is kind of some guesswork now. And this is where you can't know for sure until you've tested it on your starter bot once you get the kit. But it's a good place to start and you have the code for it there. So now that we want those positions, right? We want this position, the starting position. We want the collect position. And then we want a delivery position for the chambers and for the baskets. So now, if we go back into our code, over here, what we want to do is we want to create target positions for each of those things, right? And the way we can do that is we can use a variable again. So we'd say double, so we'd say collect position, right? And now we can set this to a value in degrees. So the collect position we said was probably around 250 degrees from the start place, right? And then I'm going to copy this a few times because we need 4. So we need the collect position, we need the start position, and we know the start position is just 0, right? And then we need delivery for the basket. And then delivery for the chamber as well. And the delivery for the basket is, and they're both going to be quite similar. So they were about 170 because they're not quite a full rotation. And so now these stores the target positions for each of the arms in degrees, right? So now what we want to do is we say the arm ticks per degree. So that's saying for every degree the arm travels in real life or on the actual robot, how many ticks does the motor measure, right? So the way we can convert these target positions in degrees to ticks that the motor can understand is we can say the value in degrees times the arm ticks per degree. So that's gonna give us the amount of ticks, and we don't really need that because it's 0. The amount of ticks the motor needs to move, or the target position of the motor in ticks, which is something it can understand, right? And then what we can do in here, now that we have the target position and we're saying the motor is run to position, we wanted to go to a position, what we can say is we can say, okay, what button do we want the driver to be able to press to go to each position? So let's say, okay, we want to use the A button on the controller to go to the collect position of the arm, right? So what we can do is we'll say if, so this is saying if the gamepad 1, which is the driver input, right, dot A. So this is saying if the driver presses gamepad 1.a, then we can say set arm motor, right, dot set target position. And we can set target position to collect position. Now we actually need to change this value to an int because motor encoders are only able to read an int, right? Which means they can't have any decimal points in their reading. We need to use ints for these variables instead of doubles, because doubles allows for the value to have decimal points, right? Like 0.5 or 23.3 or random numbers like that. But integers are only whole numbers, so like it can only be a 23 or a 200 or anything. It can't have any decimal points. And encoders can only understand that. So then we say arm motors are set target position to collect position, right? So that will mean that the arm will move to the collect position, which in the case of this is 250 degrees, right? The last thing that I want to do here that I forgot is when you first say run to position, you need to set the target position to start, just to make sure it stays in the same place. So that's basically all the controls you need. It's a lot of variables up here to store the positions, but this is a much better way of storing the positions because if you put the actual numbers in here, if you say, for instance, okay, when we want to go to the collect position, we're going to set it to 250 times the arm ticks per degree, right? And that means, and this is going to get mad because it's the double again. And this means that every time, if you need to tune this value, say 250 is not right, it's not close enough to the ground, you need it to be 255, then you have to come down into the code and find the specific value and go, oh, 255. But now in here, you can actually say, you can just say collect position. And then you know in the collect position up here, you just change it here. And if you're using it lots of places in the code, it'll change in all those places in the code without you having to go find them all, right? I think we are pretty much over time now, but we've managed to cover quite a lot in this session. So before we finish off this session, do we have any questions about the code so far, or just anything about the starter kits in general at this point? Okay. If not, then that's cool. I'll end here for today. What I'll do is I will post the recording of this session on the Discord as well, the YouTube video for this recording, so you can go back and look at it. What I would suggest is start working through this, not necessarily go line by line for everything I've done, but kind of follow the process of, I'll also send the link for the starter kit, link for the Gobilda starter kit, so you can go look at their stuff, and then you can go, okay, here's the hardware, how do you think I should control it? And what I've done here is just, it's more showing the process of how you work through it than actually the specific solution. Because your specific solution does not have to be exactly what I've shown here. It can be whatever you would prefer in terms of controlling this. Because there are lots of other ways you could do it that will achieve a similar outcome. But these are just one of the ways that you could do it. And then in next week's session, I'll finish up with the actual like gripper code and the wrist code on the end of the arm with the servos. And then probably do another session of that about, okay, now with this hardware, we've got Telia for it, but how would you actually control it to do an autonomous or something like that? If people are interested, I I can possibly run a session in the middle of the week where we can just hop on the Discord VC. And if any of you have specific issues with your code that you're working on or anything like that, I can help you. So yeah, I'll probably send out announcements at some point if people are keen. I don't know if that sounds helpful. So you can kind of work at it in the next few days, and then on maybe Tuesday or Wednesday next week, we can hop on a Discord call. And instead of me just generally talking through the concepts or the process, I can look at some of the stuff you've tried and issues you might have and see if I can help you with them. But yeah, that's pretty much it for today's session then. If there are no questions, I'll stay on here for like 2 more minutes or a few more minutes in case people have questions. But thanks very much for joining, and I will send out the recording and the StarterBot link to the StarterBot stuff in the next half an hour or so. Yeah, thanks very much, guys.
Good afternoon.
Hello? Yeah?
Hi, yes. I have a quick question that I'd like to clarity on, which regards to where do we upload the code to? Do we upload it to the controller, or we create some kind of an app for the cell, maybe the mobile phone, and then kind of like control the robot?
Yeah, so wait, yeah, okay, my audio is working. I can just quickly show you quickly how the wiring looks for the robot. So basically in Android Studio, when you download it and you get the SDK set up, that SDK is actually the Android app that runs for you. So you don't have to do any of that setup. Once you've programmed kind of what I've shown you, you can just upload it to the robot, and I'll show you what I mean by that now. If you go, wait, where is it? Here, and configuring this. So here's basically what it's going to be like, right? This thing over here called the control hub. This is what's going to be actually on your robot. And this you can see here on the sides. You've got your ports. On this side, you've got motor ports. This side, you've got servo ports. And these are sensor ports. And this is actually what's the brain of your robot. This is what you would upload your code to from Android Studio. It's actually basically a packaged Android phone. So it runs an Android app on it. But you don't have to worry about actually programming or anything. Like I said, that's already done. And then this phone over here called the driver hub or the driver station connects to this, which is the robot's brain and is on the robot. And this allows it to tell the robot or the control hub what program it should be running, right? Does that make sense?
Yes, makes sense so far.
So that's basically it then. You upload code to this control hub, and then when you connect to the control hub with this phone or the driver station, you'll be able to see the programs you wrote in Android Studio, and you'll be able to run them from this phone. And this is where you connect your gamepad to, right? Your controller, which is where the drivers control with. So that's basically the whole setup then. You just take your code from Android Studio, like I was showing you, you upload it to the control hub, and then you'll be able to see those programs on the driver station where the drivers can choose what programs to run.
I thank you.
Sure. Oh, GitHub is a place not worked in yet. Can you send us a good starter video? Yeah, for sure. I don't have one like off the top of my head right now, but I have got a few I can find for sure. So I can add that in to the announcement I'll put out in the next half an hour. Um, that's helpful. And then it was also said, sounds very helpful. Just wish we could test. The session was very well done. Yeah, thanks very much for that. Yeah, the testing is a bit of a pain that the starter bots have not come yet. The starter kits, sorry. But yeah, the majority of them have actually been shipped already. I think yeah, about half of them, so not the majority. Half of them have been shipped, so they'll be there. They'll be arriving in South Africa in the next week or so. I'm not sure how fast they'll get through customs, but hopefully they'll be quick, and then you guys can start testing in the next few weeks. So yeah, that's very exciting. I'm very excited to see what happens there. But yeah, I think that closes it for the meeting. Thanks everyone for joining. Okay, let's dive into this.